Now let's take a look at the radioactive decay data chart found on the front cover of your reference table. This chart gives you everything you need in order to work through a radioactive decay problem. It's divided into 3 sections, so let's go through each in turn. You start with the left-hand section labeled Radioactive Isotope. Now, to you and me, that means this is the unstable parent element, the one that will change over time. And you'll notice, at least for our purposes here in earth science, there are 4 parent elements that we're going to be taking a look at. They are carbon-14, and the number, by the way, is really important here. Carbon-14, potassium-40, uranium-238, and rubidium-87. Okay, each one of these will change into a more stable daughter product in a regular and predictable amount of time. Now, what about that stable daughter product? Well, that too is given to us in this chart, but now in the center section. The center section that's labeled disintegration, or I like to remember, that is the decay in radioactive decay, because it simply means the change. And we see that on the left-hand side, in each of these sections, you'll see, there's our carbon-14, potassium-40, uranium-238, rubidium-87. Those are what we have recognized as the parent elements. So we have the parent, but then an arrow which shows us the change, the disintegration, the decay, into, now at the other end of the arrow, the stable daughter product. And so the daughters are listed here for each of our parent elements. Carbon-14 changes into nitrogen-14. Potassium-40, now it looks like there are 2 arrows here. There's actually an intermediate product and then the final product. The final product here is the argon-40. The middleman is the calcium-40, but you have them both listed here. Uranium-238 changes into lead-206, and rubidium-87 into strontium-87. All right, so you've got in that center section, then, the parents and the daughters given to you. Well, there's only one further piece of information that you need, and that is that regular amount of time that it takes for the changeover from parent to daughter to occur. And that regular amount of time is what we refer to as the half-life. Okay. Now, sometimes people say half-life. That's an odd term. Well, it might sound like it is, but it really isn't. If we look at the actual definition of what a half-life is, a half-life is the amount of time that it takes to change half the mass of the parent into the daughter. So every time we go through this period of time listed in the 3rd section of this table, half the mass of the parent changes into the daughter. Over time, the amount of parent gets halved and halved and halved, so it gets smaller and smaller and smaller each half-life, and the amount of daughter gets greater and greater and greater because it increases each half-life. Now, what half-lives what amounts of time are we talking about for the half-life? Well, for carbon-14, it is the one on our chart that has the smallest half-life. 5.7 times 10 to the 3rd is 5,700 years. Carbon-14, because it has such a small half-life, is used to date things that are more recent events, going back to maybe 50, 70,000 years ago. And when we start looking at the other radioactive parents, we're going to see their half-lives are way, way, way longer. Potassium-40 has a half-life of 1.3 times 10 to the 9th years. That is equivalent to 1.3 billion years. That's a big change from 5,700 years for carbon-14. Uranium-238 has a half-life of 4.5 times 10 to the 9th years. That's like saying 4.5 billion years. Yeah, really, really close to the age of the Earth. Matter of fact, uranium-238 is often the preferred method to date the age of the Earth. And rubidium-87 is 4.9 times 10 to the 10th. Notice that exponent is bigger. So that would be equivalent to 49 billion years. So you've got in this chart the parent, the changeover from parent into daughter, and in the third column, the half-life, the amount of time it takes for half the mass of the parent to change into the daughter. So what do we do with all this information? Let's try a sample problem or two. Here's our data table again, okay, just so we could refer to it. And we'll take a look at two questions. The first sample. It says a sample of wood that originally contained 200 grams of carbon-14 now contains only 50 grams of carbon-14. Approximately how many years ago was this sample part of a living tree? All right, so first thing you say to yourself is what I'm looking to find is how many years ago. Ultimately, I need a number of years. What do they give me? They tell me I'm starting with a sample of carbon-14. And we note that carbon-14 is the parent, all right? It's going to decrease over time. How much carbon-14 did we start with? 200 grams. So we had 200 grams of our parent carbon-14. But now, after a certain amount of time that we'll figure out, there's only 50 grams of carbon-14. So I have to figure out, well, how long did it take me to get to the 50 grams of carbon-14? Well, you and I and our chart speak the language of half-lives. So let's use the definition of half-life to figure out how many years this is going to be. A half-life is the amount of time it takes for half the mass of the parent to change into the daughter. So let's just count it down. If we start with 200 grams carbon-14, after one half-life, how much of the parent are we going to have left? Well, we're going to cut that 200 grams in half. We will have 100 grams of parent. Okay, still not where I need to be. Let's take it one more half-life. If I go one more half-life for a second half-life, that 100 grams gets cut in half again. And then we wind up with the 50 grams that we needed to be at. A total of 2 half-lives. That's great, but it's not a number of years. So let's make it years. If we say 2 times, how many years was a half-life of carbon-14? 5,700 years. We wind up with our final answer, which will be 11,400 years. That's our answer, okay? 11,400 years. All we did was take the information they gave us, which was mass of the parent, keep having it until we arrive at what we want it to be at, the 50 grams, count the number of half-lives, take that number, multiply it by the value of half-life that we find in our chart. So there's your answer, 11,400 years. Let's try another question. A sample of potassium-40 is determined to be 3.9 billion years old. If the original mass of potassium-40 was 300 grams, how much argon-40 is now present. Interesting in that two things. First off, we're now being asked a how much question, so our answer is going to wind up being a number of grams. But they're starting us off with apparent potassium-40, and ultimately the how much that we're interested in is argon-40, which is a daughter. They think they're going to trick us, but they won't. So I say, let's track the parent information, and then we'll be able to see the flip side of that coin, which will always be the daughter. Now, you and I do speak the language of half-lives, but they're giving us the value of age of that potassium-40 as 3.9 billion years. Well, to figure out the number of half-lives, all I need to do is take that 3.9 billion years and divide it by the half-life of potassium-40, which is 1.3 billion years. My billion years cancel out, and the math is usually this easy. 3.9 divided by 1.3 gives me 3 half-lives that have passed in order for this change to occur. So let's again count it out just like we did with what we saw in sample question number 1. If we started with 300 grams of the potassium-40, in one half-life, that 300 changes to 150 grams. In 2 half-lives, that 150 changes to 75 grams. I'm still not where I need to be, right? I want 3 half-lives, so let me go one more. My third half-life cuts that 75 grams in half again and gives me 37.5 grams of my parent, right, of my potassium-40, because that always decreases over time. So I know out of my original 300 grams, 37.5 grams is still potassium-40. So how do I figure out how much is daughter? Well, remember, the 300 grams of the total mass is never going to change. It just gets divided between how much remains parent or how much changes to daughter. So if I know that 37.5 grams changed into the parent, then whatever is left over must be daughter. And what is left over when we take 300 grams minus 37.5, we are left with 262.5 grams, and that will be the daughter, and that will be the argon-40. So there's our answer. How much argon-40 is present after 3 half-lives? 262.5 grams. If you always work the parent in counting down, just remember, whatever's not parent must be daughter, and the total mass never changes. All right. That one was a little bit more involved, but still follows in the process of just kind of counting down. So I am sure if you a little bit of practice, you will be terrific at this.